oyster shells into Charlotte Harbor today to help boost water quality and help our fish and anglers. The shells act as a natural filter to get toxins out of the ecosystem.
For 17 years, trucks rolled toward the Florida coastline carrying something most people would call garbage. Not fish, not gravel. Oyster shells, cracked, sun-bleached, reeking faintly of the restaurants and seafood houses they'd been scraped from. 500,000 tons of them, eventually, hauled out onto barges and tipped into the Gulf of Mexico. To anyone watching from shore, it looked like the state had lost its mind. Dumping waste into the ocean has a name, and it isn't conservation. But what grew out of that decision would end up rewriting how scientists think about rebuilding a dying coastline, and it would do it faster and stranger than anyone involved was prepared for. The idea started from a problem nobody wanted: mountains of shell waste with nowhere to go. Seafood processors across Florida were paying to haul the stuff to landfills, where it sat, inert, doing nothing for anyone. At the same time, the state's oyster reefs, once sprawling underwater cities that filtered the Gulf and fed entire fishing economies, had collapsed. Decades of overharvesting, pollution, and coastal development had stripped the seafloor bare. Without old shell to settle onto, baby oysters had nowhere to attach and grow. It was a dead loop: no substrate, no oysters, no reef, no substrate. Someone in Florida's wildlife agency looked at those two problems side by side and asked an obvious but risky question. What if the waste was a fix? What if the discarded shells could be put back into the water, not as trash, but as a foundation for the reefs that used to be there? It sounded almost too simple, and that simplicity is exactly what made critics furious. Environmental advocates warned that dumping 500,000 tons of anything onto the Gulf floor was reckless, whatever the intention. They pointed out that shell piles could smother existing marine life, choke soft-bottom habitats, and disrupt currents in ways nobody could predict. Commercial and charter fishermen, many of whom had fished the same waters their fathers and grandfathers had worked, were just as skeptical. They'd watched government projects promise ecological miracles before and deliver mud and disappointment instead. To them, this sounded like another one, dressed up with better marketing. The agency pressed forward anyway, betting on a simple logic: the shells were headed for a landfill regardless. If there was even a reasonable chance they could function as reef base instead, it was worth trying. Between the mid-2000s and the mid-2020s, deposition sites were mapped out along stretches of Florida's Gulf Coast, particularly around Cedar Key, and the shell drops began. Nobody, including the biologists running the program, expected results anytime soon. Artificial reef projects using concrete, tires, or sunken vessels typically take years to show meaningful biological activity, if they ever do. So when monitoring teams returned to the first deposition sites less than 2 years later, they were bracing for silence: a lifeless scatter of shell on an empty seafloor. Instead, they found something already alive. The transformation didn't start with fish or even with oysters. It started with something invisible. Within days of hitting the seafloor, the shells were being colonized by bacteria, forming thin biofilms across every surface. That might sound unremarkable, but it was the opening move in an entire ecological chain reaction. Those bacterial films began converting bare calcium carbonate into something living organisms could actually use: a functional, textured microhabitat instead of dead, inert shell. There was chemistry at work too. Oyster shell is mostly aragonite, a form of calcium carbonate that dissolves gradually in seawater, releasing calcium ions into the surrounding water. That slow release created tiny pockets of more alkaline water directly around each shell, precisely the kind of chemical environment that barnacles, tube worms, and young oysters need in order to attach and begin building their own hard structures. In effect, the shells weren't just sitting there waiting to be used. They were actively altering the water around them to make colonization easier. Within weeks, diatoms and microalgae had moved into the biofilms, forming the first rung of a food web. Tiny crustaceans and drifting mollusk larvae arrived to graze on that algae, and their presence drew in the first juvenile fish looking for an easy meal. Each new arrival fed the next, building outward from nothing. None of this required human intervention. It was simply what happens when you finally give marine life a hard surface to work with on a seafloor that had only ever offered soft, shifting sand. Sand can't support a biofilm the way shell can. It has no chemistry to offer, no fixed structure for anything to grip onto. The shell deposits had solved that limitation instantly, just by existing. The real turning point came when oysters themselves returned. Oyster larvae, known as spat, drift through the water column, searching for hard surfaces to settle on. In a healthy system, that surface is provided by older shell, layers of it built up over generations, forming the reef itself. But with Florida's natural reefs gutted, spat had nowhere left to land. The new shell piles changed that instantly, acting as concentrated landing zones positioned exactly where Gulf currents would carry drifting larvae. Within the first year, researchers documented juvenile oysters attaching to the deposited shell in numbers well beyond what anyone had projected. By the second year, those juveniles had matured into breeding adults, producing new larvae of their own, larvae that settled onto the very reef their parents had helped build, adding a second generation on top of the first. What began as a human intervention had become something closer to a self-sustaining cycle. By the third year, some monitoring surveys were recording several hundred oysters per cubic meter of shell substrate, compared to almost none on the surrounding bare seafloor. And because oysters die, decay, and leave their own shells behind, the reefs weren't just growing thicker, they were also spreading outward, beyond the original footprint of the dumped material. That shift was visible enough that it started changing minds on the water, not just in scientific reports. Charter captains who had originally opposed the shell program, who had argued publicly that it would ruin fishing grounds their families depended on, began reporting fish activity around the new reef sites unlike anything they'd seen in decades. Redfish schools holding steady in the current, snook working the edges, structure where there used to be nothing but flat, empty bottom. For fishermen who make their living reading the water, that kind of change is hard to dismiss, and several of the loudest early critics eventually became some of the program's strongest advocates. The fish numbers backing up those observations were dramatic. Within a couple of years of the reefs establishing themselves, surveys near the deposition sites recorded biomass increases of several 100% compared to unrestored control areas, along with a sharp rise in species diversity. Crucially, researchers were careful to distinguish this from what typically happens with man-made reefs like sunken ships or concrete structures, which tend to simply attract fish that already exist nearby, concentrating a population rather than growing one. The oyster reefs were doing something different. The increases were driven largely by juvenile fish that had been born and had survived in that specific habitat, not fish drawn in from elsewhere. The reefs weren't just gathering marine life. They were producing it. As the reef structures matured, the ecological cascade kept climbing. Octopuses took up residence in the gaps between shell clusters. Sea turtles began foraging along the reef edges. Dolphins were observed hunting there methodically, working the dense schools of fish the reefs now supported. Every new species that moved in reinforced the food web beneath it, making the whole system more stable and more resistant to disruption with each passing season. And the benefits weren't confined to fish and structure. A single adult oyster filters somewhere between 30 and 50 gallons of seawater a day, pulling out excess nutrients, suspended sediment, and pollutants as it feeds. Multiply that by the growing oyster populations across the restored reefs, and you get an enormous, continuously operating water treatment system. One that required no machinery, no electricity, and no maintenance budget. Water clarity around the reef sites improved measurably within a few years. Clearer water let more sunlight reach the seafloor, which allowed seagrass beds, critical nursery habitat for juvenile fish, manatees, and sea turtles, to expand into areas that had previously been too murky to support them. Improved water quality and expanding seagrass reinforced each other, creating a second feedback loop layered on top of the first. Then came the test nobody planned for. In September 2017, Hurricane Irma tore across Florida as a powerful Category 4 storm, driving destructive storm surge and waves along the Gulf Coast. Communities near the restored reef sites braced for the kind of shoreline damage these storms reliably cause. When damage assessments came in afterward, shorelines protected by the restored oyster reefs had experienced notably less erosion than unprotected stretches nearby. The dense, irregular, three-dimensional structure of a living reef, layers of oyster clusters piled on shell, rough and uneven, had absorbed and broken up wave energy before it reached the shore, acting as a natural buffer that smooth seawalls and bare beaches simply couldn't replicate. That resilience pointed to something traditional coastal defenses can't offer. The reefs actually get stronger after a storm, not weaker. Storm disturbance triggers fresh larval settlement, and each new generation of oysters adds height and structural complexity to what's already there. A concrete seawall cracks under repeated battering and eventually needs replacing. A living reef, by contrast, repairs and rebuilds itself using the very forces that damage it. By the early 2020s, some of the oldest deposition sites had roughly doubled in area since the original shell drops, expanding outward on their own without any additional human input. Structurally, they'd also become far more complex, no longer loose piles of shell, but elaborate three-dimensional habitats full of overhangs, crevices, and interlocking surfaces supporting dozens of distinct microhabitats for crabs, fish, and invertebrates. Researchers have also found that dense oyster reefs help lock organic carbon into their shells and the surrounding sediment, adding a climate dimension to what started as a habitat restoration project. What began in the mid-2000s as a contested, almost desperate use for seafood waste has become something closer to a working model. Other Gulf states have since launched their own shell recycling and reef-building programs, and the underlying idea that so-called waste material can be redesigned into functional ecological infrastructure has drawn interest from coastal engineers well beyond Florida. The shells that went into the Gulf were never engineered with precision. They were leftovers, dumped with no guarantee that anything useful would come of it. What formed instead was a living, self-repairing, self-expanding system that has outperformed almost every artificial reef built with far more careful planning. Proof that sometimes the most effective fix for a broken ecosystem is simply giving nature back the raw materials it needs and getting out of the way.